Application: Tangents in concentric circles. Welcome, everyone. Today, we are going to dive into a very interesting topic in geometry: the application of tangents within concentric circles. In this subsection, we are going to explore a specific geometric configuration where we have two concentric circles, meaning circles that share the exact same center point. As we move through this lesson, we will examine the fascinating way the properties of tangents and chords interact when one circle is nested perfectly inside another. By the end of this session, you'll see how we can use these relationships to even solve complex problems involving lengths and distances. Understanding the basics. First, we have concentric circles. You can think of these like a bullseye on a target. We say two or more circles are concentric if they share the exact same center point, which we will denote with the capital letter O. Next, let's look at the chord of the larger circle. If we have our larger circle, which we'll call C1, a chord is simply a straight line segment where both endpoints sit right on the edge, or the circumference of that larger circle. Finally, we have the tangent to the smaller circle. Now, remember we have a smaller circle nested inside, which we'll call C2. A tangent is a special kind of line that just grazes the edge of this smaller circle, touching it at exactly one single point. Now that we've introduced our topic, let's establish some fundamental definitions so we're all on the same page before we dive into the geometry. Keep these three definitions in mind, because in the next slide, we are going to see how these elements actually interact with one another. Conceptual breakdown. Now that we have defined our basic terms, the concentric circles, the chord, and the tangent, let's bring them all together into a single geometric scenario. Imagine we draw a chord, let's call it a B, across our larger circle, which we've labeled C1. Now, here is the key part. We draw this chord specifically so that it just grazes or touches the edge of our smaller circle, C2, at a single point, which we will call point P. To help us make sense of how this chord, this tangent, and our radii all interact, we are going to break the problem down into a few logical steps. Step 1. Identifying the tangent. Now that we have set the scene with our two concentric circles, let's move into our first logical step. Take a look at the chord, line segment a B, which we've drawn across the larger circle. Notice how this line just grazes the edge of our smaller circle, circle 2, at exactly one single point, which we've labeled point P because it touches the smaller circle at only that one specific point and doesn't pass through its interior. We can apply the formal definition of a tangent. Therefore, we can officially state that the line AB is a tangent to the smaller circle 2 at point P. This is a crucial realization, because it allows us to use all the specific properties of tangents that we are about to discuss in the next step. Step 2. Applying the tangent radius property. Now that we have identified that the line segment AB is indeed a tangent to our smaller circle, let's move on to step 2, where we apply a fundamental property of circles. One of the most important rules you need to remember is that a radius is always perpendicular to the tangent at the exact point where they meet. So, if we take our center, point O, and draw a radius straight to the point of contact, which we've labeled as point P, this creates a very specific geometric relationship. Specifically, the line segment OP is perpendicular to the line segment OB. This perpendicularity is the key piece of information we need to bridge the gap between the two circles and solve the problems we'll see later. Step 3. Applying the chord property. Now, let's shift our focus slightly. Up until now, we've been looking at the line segment OB as a tangent to the inner circle, but let's look at OB from the perspective of the larger circle, which we've labeled C1. In this larger circle, OB is actually a chord. Now, there is a very important geometric theorem you need to remember for your exams. It states that any perpendicular line drawn from the center of a circle to a chord will bisect that chord, meaning it cuts it into two equal parts. Recall what we established in step 2 of our breakdown. We proved that the line segment OP is perpendicular to OB. Because this perpendicular relationship exists, we can logically conclude that the point P must be the exact midpoint of the chord OB. This is a crucial realization, as it tells us that the two segments, AP and BP, are perfectly equal. Step 4. Final conclusion. Now, let's bring everything together for our final conclusion. Because we established in the previous step that the perpendicular line from the center bisects the chord, we know that point P acts as the exact midpoint of the segment OB. This means that the length of the segment from A to P is perfectly equal to the length of the segment from P to B, which we can write mathematically as a P equals BP. This symmetry is the key piece of information we'll need when we move into our practical example in the next slide. Real-world example, the archery target. Now, to help you visualize these geometric properties in a real-world context, let's step away from the abstract diagrams for a moment and look at something more familiar, a professional archery target. As you know, an archery target is made up of several concentric circles, all sharing the same center. Let's apply our notation to this target. Suppose the innermost gold circle represents our smaller circle, which we've called C2, and the outer red circle represents our larger circle, C1. Now, imagine an arrow or a straight line drawn across the red circle. If this line passes through the red circle but just barely grazes the very edge of the gold circle, we can say that this line is a tangent to the gold circle. Based on the geometric principles we just discussed in the previous slides, there is a very specific result here. The exact point where that line touches the gold circle will divide that line into two perfectly equal halves. This isn't just a neat trick for geometry class. This principle of tangency and symmetry is actually used extensively in precision engineering and mechanical design to ensure that circular components are perfectly balanced and symmetrical. Now that we've seen how this works in practice, let's move on to a worked example where we will use numbers to calculate an actual length. Worked example. Now that we have understood the geometric principles behind how tangents and chords interact in concentric circles, let's put that theory into practice with a worked example. Here is the problem we are going to solve. Imagine we have two concentric circles. We are given that the radius of the larger circle is 5 centimeters, and the radius of the smaller circle is 3 centimeters. Our task is to find the total length of the chord of this larger circle, specifically the one that is tangent to the smaller circle. As we move to the next slide, we will break this down step by step, using the properties of right-angled triangles that we just discussed. Step-by-step solution. First, we need to identify our given values from the problem description. We are looking at two concentric circles, so we have the radius of the larger circle, which we can \textcan$ call OA, equal to 5 centimeters, and the radius of the smaller circle, which is OP, equal to 3 centimeters. Second, we need to establish a right-angled triangle to work with. Remember from our earlier conceptual breakdown that a tangent is perpendicular to the radius at the point of contact. Since the line segment OP is the radius meeting the tangent line AB at point P, we can conclude that triangle OPA is a right-angled triangle, with the right angle located at point P. Third, this right-angled triangle allows us to apply the Pythagoras theorem. Looking specifically at triangle OPA, the theorem tells us that O² equals OP squared plus a P squared. Plugging in our known values, we get 5 squared equals 3 squared plus a P squared. This simplifies to 25 equals 9 plus a P squared. To isolate a P squared, we subtract 9 from 25, which gives us a P squared equals 16. Taking the square root of 16, we find that the length of a P is 4 centimeters. Finally, we must calculate the total length of the chord. Don't forget the property we discussed in step 3 of our breakdown. The perpendicular from the center bisects the chord. This means that the segment a P is exactly half of the total chord AB. Therefore, a B equals 2 times a P. Since a P is 4 centimeters, the total length of the chord AB is 8 centimeters. Now that we have the problem stated, let's walk through the solution step by step. Final answer. And there we have it. After applying the Pythagorean theorem and doubling the length of the segment, we arrive at our final result. The length of the chord is 8 centimeters. This completes our worked example, and we can now move on to review the key principles we've used to solve this problem. Key takeaways. First, remember the fundamental connection we established. Whenever you see a chord of a larger circle that just grazes the edge of the inner circle, you should immediately recognize that this chord is, by definition, a tangent to that smaller circle. Second, keep this geometric relationship in mind. The radius of that smaller circle meets the chord at the exact point of contact at a perfect 90-degree angle. In other words, the radius is perpendicular to the chord. Third, because of this perpendicularity, a very helpful property comes into play. The point where the radius meets the chord actually bisects it. This means the point of contact splits our chord into 2 perfectly equal segments. Finally, if you are faced with a numerical problem, remember that these elements form a right-angled triangle. This allows us to use the Pythagoras theorem to find any missing length. The relationship can be expressed as r squared equals r squared plus the quantity, 1/2 of the chord, all squared. If you can master this formula, you can solve almost any problem involving these concentric configurations. All right, class, we have reached the end of our lesson. Before we move on to look at some common pitfalls to avoid in the next slide, let's quickly recap the key takeaways from today's topic on concentric circles. Common mistakes. First, watch out for confusing the radii. It is very easy to accidentally plug the radius of the larger circle into your calculations where you actually need the radius of the smaller circle. Always remember, the distance from the center, point O, to the point of contact, point P, is always the smaller radius. Second, a very frequent error is forgetting to double the length. As we saw in our worked example, using the Pythagorean theorem only gives you the length of the segment from A to P, which is just half of the chord. You must remember to multiply that value by 2 to find the full length of the chord, segment AB. Finally, do not assume that the chord is a diameter. Unless the problem explicitly states that the chord passes through the center, you cannot assume it does. Remember, because this chord is a tangent to the inner circle, it must maintain a specific distance from the center, which is equal to the smaller radius. Now, before we conclude our lesson, I want to highlight some common pitfalls that students often encounter when solving these types of problems. Being aware of these will help you avoid losing marks on exams. Keep these points in mind, and you will be well on your way to mastering applications of tangents in concentric circles.